Alright, so now we're moving on to problem number 3419 on Leetcode, which is marked as a medium level problem, and it is minimize the maximum edge weight of a graph. So this is actually a very good problem, and let us go with the problem statement first. So you're given two D integers n and threshold, as well as a directed weighted graph of n nodes numbered from 0 to n minus 1. The graph is represented by a 2D integer array edges, where edges of phi is equal to ai, bi, w of I, which indicates that there's an edge between edge going from node A to B with an edge cost of w, so the weight is w. So you have to remove some edges from this graph, possibly none, so that it satisfies the following conditions. That is, node 0 must be reachable from all the other nodes. The maximum edge weight in the resulting graph is minimized. Okay, so node 0 must be reachable, and the second condition is maximum edge weight in the resulting graph is minimized. So whenever you hear something like maximum being minimized or minimum being maximized or shortest path being maximized or longest path being minimized, right? Whenever you hear these kind of cues in the question, uh, you must think of basically binary search here, because that will optimize the problem. So binary search, basically you should always keep in mind that whenever you're seeing these cues, mostly the problem would involve you using binary search. I mean, it might not be necessary, but you can still try for a binary search, because that would make the problem being solved optimally, right? So this is another this is the queue that we need for binary search, so we are sure that binary search would be used. And then each node has at most threshold number of outgoing edges, right? So each node must not go above the threshold value for their outgoing edges, right? So their out degree should be less than equal to threshold, because it is at most threshold. So less than equal to. Now return the minimum possible value of the maximum edge weight after removing the necessary edges. If it is impossible for all conditions to be satisfied, we return -1. Now this is our first example, n is equal to 5, and we have been given our edges vector of int type. So threshold is also 2. So let us form the graph first. This is the graph. Between 1 to 0, we have a directed edge of weight 1. Then this is basically the graph that is formed from this edges vector of vector, right? So now we need to remove that edge which has the maximum weight, right? So we basically need to return the minimum possible of the maximum edge weight after removing the necessary edges. So we always take the maximum edge weight. So 2 is the maximum edge weight among this among all the edges in the graph. So we remove this edge, and the maximum weight now remaining has been minimized, and it is equal to 1. Threshold is equal to 2. That means that from every node there must be at most 2 edges outgoing. So it cannot exceed 2. There can be 1 as well, and there can be none as well, but not less than not greater than equal to 2, right? So that condition is being met. Also 0 is reachable from every other node, right? You see 1 can reach here. This node has been removed, right? This edge has been removed, but 2 can also reach here from 1. Then 4 can also reach it, and 3 can also reach it. So basically, are all the conditions being met? Yes, that node 0 is also reachable from all the other nodes. Maximum edge weight in the graph is being minimized, definitely, and each node has at most threshold outgoing edges. So the 3 conditions are being met. Now let us move to the second example. So in this one, we have something like this: 0 to 1, we have 1 as the edge weight. Then 0 to 2, we have 2 as the edge weight. Then 0 to 3, we have 1 as the edge weight again. Then 0 to 4, we have 1 edge weight. Then 1 to 2, that is 1 to 2, we have 1 edge weight. Then 1 to 4, we have another edge weight, that is 1. So now you see the maximum edge weight is actually 2, right? So we need to minimize it, so we remove this edge. Once we have removed it, right, we check, are we able to reach 0 from all the other nodes? In fact, even if this edge wasn't removed, you see that any node could not reach 0, because 0 is the source node here, and there is no incoming edge to 0. So this would obviously be -1. We return -1 because it is not possible to reach 0 itself in the starting condition itself. So we return -1. So we would keep a check that if it is impossible to reach node from 0, node from any other nodes, we return -1. Right. Now next example, let us go through this. So we have this as our graph that has been formed, and we extract the maximum edge weight, that is 5 here. So we check if we remove it, and we also remove the edges 1 to 3, that is this edge. Are we able to reach 0 from all the other nodes? So we check from 1. Definitely there's an edge from 1 to 2, then 2 to 3, then 3 to 4, and 4 to 0. So we are able to reach node 0 from 1 as well as 2, as well as 3 and 4 as well. So basically we are able to reach 0. from all the other nodes, even after removing these edges. So basically, we have minimized the maximum edge weight, and the maximum edge weight now remaining is 2, since we have removed 3 and 5 edge weights from the graph completely. And threshold is 1, so that is also being met, that there's only one single outgoing edge, since these edges have been removed. So there's only one outgoing edge. At most, we need to keep threshold number of edges, right? So that is being met. So what is the intuition behind it? So let us go through my problem. So instead of checking reachability from each node to 0, that would require us, we are checking the reachability from each node to 0. So that would basically require us calling, BFS multiple times. So that would increase the complexity. So instead of checking that reachability from each node to 0, we reverse all the edges, and then we only need to check if all nodes are reachable from node 0, right? So we're thinking in the reverse fashion, that if we reverse the edges from 0 to all the other ones, right? So now we only need to call one BFS, right? That is on node 0, and check if all the other nodes are being reachable from node 0 using BFS DFS. So we perform BFS to check if all nodes can reach 0, reverse graph approach. So we reverse the adjacency list. First intuition is that. Second is that we use binary search on the answer, edge weight. For a given threshold mid, we keep only the edges that have weight less than equal to mid and check if all nodes are reachable from 0. If yes, we try smaller mid values. If no, we increase the mid value, right? Now the approach is reverse the graphs. Firstly, for every directed edge u to v and weight, we store v to u and weight in adjacency list, which allows us to start BFS from node 0 and verify the reachability. Then BFS check for a given mid value, we traverse the graph from node 0 using only edges where weight is less than equal to mid, right? That is the condition given to us, that it should be less than the threshold value. So if after BFS all nodes are visited, mid is valid. Now binary search, let maximum weight is equal to max of edge weights be the upper bound. Binary search mid in the range 0 to max weight. The smallest valid mid is our answer. Now the complexity, BFS complexity is O of v plus c per BFS call. Binary search complexity is O of log max weight, right? It takes O of log times the value, and total complexity is O of v plus c times the log of maximum weight, and space complexity is O of v plus c for adjacency list and visited array, right? So now let us get to the most important part, that is the code. So let us first read through this. So instead of checking reachability from each node, we reverse all edges. That is the first thing we do. Then we only need to check if all nodes are reachable from 0, right? We use binary search on the answer, edge weight. For a given threshold mid, if we only keep the edges with weight less than equal to mid and check if all nodes are reachable from 0. If yes, we try smaller mid values. If no, we increase the mid. So this is the same thing that we discussed here. Now let us start. So P is pair of, we are using the alias name for pair of increment as P, right? So let me show you where I'll be using this. So that I'll be using in our unordered map. So basically it is being used to store u to v and the weight as well. So the pair of int comma int is useful here. That is in this format, vector of p, and int is basically for the node u, that is the starting node, right? So min max weight is our function, right? So we basically are passing the number of nodes, the edges, and the threshold value that we have. So initialize, we initialize maximum weight as 0, and we declare our adjacency list, right? So from the we form the adjacency list with reversed edges to get all the nodes reachable from 0 for BFS DFS, instead of having to call BFS DFS from each node to see whether 0 is reachable from that node, right? So for each edge in edges, since there's a directed graph, we reverse the edges. So we have u as e of 0, v of e of 1, weight as e of 2. So we form the adjacency list of v to store our u. So basically we have reversed the edge from v to u. In basically classically what we do is, when we're forming a normal graph, we push back in adjacency list of u, v and weight, right? But now we need to reverse the edges, so we are taking the edge v to u as the directed edge. So we have reversed it, and we set the maximum weight as maximum of maximum weight and weight, and our answer we declare as int max firstly, and we basically performing binary search here. L is equal to 0, r is equal to max weight. So binary search on the answer, that is the weight. So while L is less than equal to r, the standard binary search we are applying. So while L is less than equal to r, mid is equal to L plus r minus L by 2. That is the standard way of writing it. If can all reach 0. So basically this is the BFS call. N, adjacency, and mid have been passed. If the BFS is returning true, if we can all reach 0, then answer would be mid, set to mid, and r is mid minus 1. That is, we have to try smaller max weight. Otherwise, if the BFS is not returning true, it is returning false, then we increase our L to mid plus 1. And finally, this is after the binary search being performed, return answer is equal to int max, return minus 1 if the answer is int max, that is, If the answer has not been updated, it means that it is impossible for all conditions to be satisfied, as if it has changed, if the answer has been updated, we return answer. Now let us get to our main function, that is bool all can all reach 0. So that is a BFS, which is taking n and the adjacency list as well as the mid value. So we declare a queue for our BFS of n type and vector of bool type visited, marking all the nodes as false. That means that they have not yet been visited. So every uh, entry has false initially. Now we're starting from 0, so we basically mark visited of 0 as true. So we start our BFS while the queue is not empty. We extract the node from the top or the front of the queue and pop it out. So for each neighbor in adjacency of node, each of the pair of, since we are storing the pair in the adjacency list, right? So this is the pair. So pair of int comma int. So neighbor is p dot first and weight is p dot second. We extract a neighbor and weight, that is the edge weight. If the weight is less than or equal to mid, that is if edge weight is less than mid, means that if it is less than the threshold value, right, and the neighbor has not yet been visited, so we can remove this edge to get a better value or a smaller value. That is, now we visit neighbor is equal to true and q dot push it inside the queue, and we check basically for each node. We're going over all the nodes. If visited of that particular node is false, that means this ith node wasn't visited, so it is unreachable from 0. In reverse, 0 would be unreachable. That means that when we reverse the edges back, 0 would be unreachable from that particular node, that is the ith node. So the condition is false. That means we return false for the whole BFS. We couldn't visit all nodes because the condition given to us is that we need to reach 0 from all the other nodes, and that is being returned as false. That is, we cannot reach from 0 to that particular node in the reversed graph. So that means we cannot reach all the nodes, right, since ith node is falling out. So that is why we return false. And otherwise, if all the conditions are true, then we return true. So that's it about the problem.